I'm going to discuss a simple example magnetisation problem. We did touch on this in lectures, but I'm going to go through it in a bit more detail and explain some of the basic background reasoning. So we have a long cylinder of radius r. There's a magnetisation m, which is kr squared phi hat. K is just a constant, r of course is the standard radius, and phi hat is the cylindrical polar coordinate, and there's no free current, so J free is equal to 0. Remember, free current is the current that we as experimenters apply to the problem, so for instance by wrapping a coil of wire around the piece of material we're measuring. So let's just sketch this briefly. And we'll see that we've got a cylinder here. When we say a long cylinder, what that means is that we're effectively assuming it's infinite, so that we can ignore the end effects, and that's quite important. So we need to find, the problem asks us to find B, the magnetic field. Let me just sketch in a sort of a light blue the magnetisation. So there is M, the magnetisation in a phi direction, so it's orbiting the pole, and of course it's uniform all the way along the cylinder, so we're going to have M in the same way everywhere here. That's just to make it clear. So there are two ways that we can think of to find B. First of all is we can use H, the magnetic intensity, and in this case of course there's no free current, so that's actually probably going to be quite helpful and useful. The second way is to use the magnetisation current densities in the material to give B. We're going to think about both of those. So let's think first of all about H. So for H, we're going to use Ampere's law, so we're going to have that the curl of H is going to be given by J free, which of course is just equal to 0. So now we're going to convert that into the integral form, and we're going to do a surface integral. So let me draw our surface up here. Actually, I'm just going to remove one of these little m's here so that I can draw the surface. So the surface is going to be inside the cylinder, at least initially. And so, of course, what we're going to say is that the surface integral of curl of H dotted with n dA is equal to 0. And n, of course, is in the z direction. Remember, please, as I'm now doing, to put axes on all of your diagrams. Let me just label that surface as S. Using Stokes' theorem, that tells us that the closed loop integral of H dotted with dl is going to equal 0. So, can we immediately deduce that H is equal to 0? Well, we can, though we probably want to examine those assumptions. So, why would we say that? Well, first of all, from the symmetry of the problem, or if you like, from the geometry, we can say that H is going to be in the phi direction. H equals H phi in the phi hat direction. That's because we're going to have currents which are going to flow along the z-axis. We can deduce that by simply looking at the magnetisation. Of course, in this case, if H is equal to 0, there are no currents, but you take my meaning. We could do the same for B, so B and H are going to be similarly related. So by symmetry, H must go around the phi direction, and it must also depend only on the radius, on little r. If this were not an infinitely long cylinder, those two assumptions, certainly near the ends, would not be valid, and we would need to be just a little bit more careful. And this is why, for instance, there's a difference between the field outside an infinite solenoid and the field outside a bar magnet. And that's something that we will continue to think about during the course. So we can say from symmetry that H must be in the phi direction. It's only depending on R. And therefore, if we can appeal to the value of B in the far field to think about what H must be, because if you're far away from the cylinder in vacuum, the two are proportional to each other. And B far away must be 0, because there is no current flowing, no Jm, and therefore, given the symmetry constraints, the only solution that fits all of those is B equals 0 and H equals 0. It's worth just working through that argument on your own and making sure that you understand it. Now if h is equal to 0, that allows us to deduce b, because we know that b is equal to mu naught into h plus m. So therefore b is equal to mu naught k r squared in the phi direction for r less than capital R. Outside the cylinder, of course, b is equal to h is equal to mu naught. So b will equal 0 for r greater than r, and let's say less than or equal to r. Okay, so that's how we find the field using h. So the maths is extremely simple. The arguments to get the far field maybe takes a little bit of thought. What about b? Well, to find b, we need to find the current densities. So let's start with Jm. That's the volume current density. That is the curl of m. Now m is only in the phi direction, so we only need the parts of the curl which involve phi. So using cylindrical polar coordinates, we get minus dm phi by dz in the r direction, plus 1 over r d by dr of rm phi in the z direction. The first term is going to be 0 because m phi doesn't depend on z, so we just get 1 over r d by dr of kr cubed, that's r times m phi. D by dr of kr cubed is just 3kr squared. We divide by r, and that gives us a 3kr in the z direction. So the magnetization volume current is flowing in the positive z direction, and it increases as you get further from the center of the cylinder. The surface current density is m crossed with n. Now the normal is just the radial direction, so we get the following. We get kr squared, and then we have phi, which is the direction of the magnetization, crossed with the radial direction. Phi cross r is minus z, so we get minus kr squared in the z direction. So the surface current density flows in the negative z direction. Let's calculate b again. So we're going to say that the closed surface integral of the curl of b, dotted with n dA, is going to equal mu naught times the surface integral. So if I said closed surface, I didn't mean closed surface. It's not a closed surface. So the surface integral of a of Jm dotted with n dA, because there's no free current density. And we're again going to say that r is less than capital R, so at this point we're not interested in the surface polarization current density. Transform that and we get the closed loop integral of b dot dl, that's using Stokes' theorem. And that's going to equal mu naught times the integral of 3kr r dr d phi. So that's converting the jm dot n into just the 3kr, and then the surface area element is r dr d phi. Now we've already said that b must lie in the phi direction and depend on r, so we can take it outside the integral. So we have b phi multiplied by 2 pi r, that's just the integral of the loop integral, that's just the loop integral around the circle. In fact, let me just write that in. Closed loop integral dl is going to equal b phi times 2 pi r, and of course we've got rid of the vector symbol on the dl there because we've done the dot product with b. And that's going to equal mu naught multiplied by 2 pi, that's the d phi, that's the phi integral, and then we've got integral of 3 kr squared dr, and that of course is just kr cubed, so it's mu naught times 2 pi kr cubed. And therefore b is going to equal mu naught kr squared in the phi direction. And so I've just done a little bit of a jump there. I've cancelled the 2 pi here with the 2 pi there, the r with the r cubed, and that gives us the same answer that we had before. It's a little bit more involved, but it's perfectly reasonable that we should have the same answer. We might want to think about the currents that are flowing and just check that they sum up to 0, because we know that this is a closed system. So let's just go back up and look at the current densities here. So we've got a surface current density, J, little jm, and a volume current density, capital Jm. When we integrate these, we need to integrate and think about the current that's flowing along the z direction, the z-axis. So for Jm, that's going to involve integrating over an area. For little jm, that's going to involve integrating over a line, so just the circumference of the circle. So let's just check the total current. And let me just draw that to make it clear what's happening. So I'm going to draw it with, I'm going to draw a circle. So we're looking along the z-axis now. So this is looking along z. We want to integrate capital Jm over the surface, that's the shaded green area, and little jm over a line, which in this case is the circumference of the circle. So that tells us that capital I, which is the total current, is the integral over the surface of capital Jm, which is 3kr, and I could now do dot n dA, but we know that J lies along the normal to the surface, and so the surface area element is r dr d phi. And then we're going to have an integral over a line, that's the red line, of the surface current density, which is minus k capital R squared, multiplied by the line element, which is going to be capital R d phi. Okay, so the radius of this circle is capital R, and so when we're going around it, the element is just capital R d phi. And it's very quick and easy to show that this sums to 0. So the first integral, the volume current density integrates to k r cubed multiplied by 2 pi, and the line integral of the surface current density integrates to minus kr cubed times 2 pi, which of course sums up to 0. That's how it should be, but it's always good to check for consistency, because that can help us to find errors.